Very good. Let's start. Any questions? Anything? Okay, I thought of talking a bit about the solutions to the homework. By now, I think everybody that wanted to submit already submitted. So let's play with question 5 of the homework that asks how many rejections could happen. And of course, I'm asking about both the minimum and the maximum, and the minimum is of course obtained where no two men has the same, no two males have same first choice. And I know that you all know it, but I'm mentioning it because we are going to use it in the next question. Because if no two men have the same choice, then of course, what does the TMA is doing? In the TMA, each male proposed to different females. There is no rejection because he is her only choice. And because of it, there would be 0 rejections. So after 1 day, we are all done. What is the maximum number of rejections? The maximum number of rejections will happen, that would be for the mean. And for the maximum number of rejections, we need to have a consensus. I think that I have like 4 spelling mistakes here, but please change randomly the S to C and something. I mean, when, let's get away from it, agreement between all males about what is the first choice, let's call her A, what is the second choice, let's call her B, what's the third choice, let's call her C, and so on. So there is consensus between all the males about the order of the females, and that I'm sure that you all wrote correctly. I hope that you also proved how many rejections do we have in this case, and if you didn't prove it, let's go over the details right now. So in the first day, we have the set of all males, M1, M2, all the way up to male N. They're all of making proposals to female A. And then she's checking her ranking. She is picking out of all the males the top without limitation of generality. Let's assume that the top will be male 1 in her own list. So she's rejecting everybody else. So far we have N rejections. So far. Next day, everybody that was rejected in the first day are making a proposal to female B, and she's picking her top choice. Again, let's assume it's M2, no limitation of generality. She has a top choice out of the ones that did reject to her, that did offer to her. So everybody else from this set that now contains only N-1 males is being rejected except 1. So there will be the number of rejections so far. I'm sorry. The first one will reject N-1. Right? That's the number of rejection that female A rejected. The second one will reject N-2 because N-1 made the proposal to her and she rejected all but 1. The next one will be n minus 3 plus dot 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 plus the second one from the bottom will make one rejection. So how many rejections do we have in general? Well, we have this little sum that tells us that 1 plus 2 plus 3 plus dot 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 n equals n minus 1 over 2. This, what happened to this sum? If I'm reading it from right to left, then I'm getting exactly this sum, except that it ends in n minus 1, not in n minus 2. So the number is n minus 1, n minus 2 divided by 2. That's the number of rejections in the worst case. N minus 1, n minus 2 divided by 2. And that's the moment that we are all enjoying from the blessing of big O and big omega. And we said, what is the dominant term here? We have n squared, that is n times n divided by 2, which is omega of omega of n squared, right? Because the number that is written here, the dominant term, is half n squared, and half, the last time I checked, was a constant. So that's a maximum number of rejections that might happen. And hopefully all of you went through this this sum. Let's think. 1 plus 2 equals, you might be right, 1 plus 2, making it 3, making it 2 times 3, and you are absolutely right. Thanks. Thanks, Danilo. So it's n plus 1, so here it will be n minus 1 times n. N minus 1 times n. But because it's n minus 1, but it's I'm only going up to n minus 1, so it's n times n minus 1 plus 1, which is n. Still, it's half n squared, which makes it omega of n squared. And hopefully you all went through this way. I mean, the fear that I have is that people said it's order of n squared, which is absolutely true, but that only shows that it will not take more than n squared rejections. It doesn't show anything about that there is a case that it could take n squared, which makes maybe our hope to find a faster algorithm useless, like hopeless. Questions?
I had a question. In my algorithm, I was able to get every woman to reject n minus 1 men, all n minus 1 men, and the way I thought about it is every day there's the same woman gets proposed by 2 people and 1 man gets rejected. So 1 man gets rejected every day, and but you don't want one of the men to propose to his last woman, because at that point she has to say yes, because there's always a pair for everyone. So essentially, I had every woman get rejected by every woman except for the last one, and then there was one guy, the very last guy, to get proposed.
I cannot tell you in real time. I don't see the bug in real time, but we had a little lemma when we talked about the TMA that says that no man is rejected by all women, right? So it doesn't contradict it.
I think I could come up with an example. I just have to try writing it out.
Okay, I'm curious to see if the bound can be worse. Could be that the bound is worse. I just don't see the example ahead of time. You, I mean, if I,
If I
what?
come up with an answer, I'll try emailing it to you after.
Okay, you're saying that every male is rejected by n minus one women? It could be.
So every
Uh,
woman rejects almost every guy, and then the very last guy proposes, and then it gets accepted. So every woman rejects n minus one men. So every guy
I
except for
see.
the very last guy to propose gets rejected by like all the women except for the last woman.
And you're saying that it's general for arbitrary n? It's
Yeah.
interesting. Okay. Uh, could be. I don't see a bug here. Uh, so yeah, it's interesting. Um, le- let's move. Other things that I wouldn't, that I'm afraid of bugs from the previous question is, of course, examples that works for 2 people, 4 people, 6 people, but it's not obvious how to generalize it to an arbitrary n. You need to specify how I can generate an example that no matter what is the n that you have in mind, I can generate an example. So I want 17 people in each set. It should be obvious how I will build an example for the 17 people and why for 17 people it will the mechanisms that you are suggesting will still work. Okay. Question 6. I always give it. I'm sure that you also solutions. It's not hard to come up with a concrete example, but I thought that a more elegant solution here would be to use question 5. And question 5, if you remember, asked us what's the minimum number of rejections that you can generate, which was, of course, if the first choice of every male are no two males have the same first choice, which will consist of, and then we are running TMA, and we don't need to prove that the result is a stable matching because we know that TMA always produce a stable matching. We proved it. Now let's switch the rules of the males and females, and now females are the ones that making proposals, and the males accept or reject. And again, now no two females will have the same first male, and if we run the TMA again, but after switching the rules, obviously the result is still a stable pairing, right? And as long as the choices of the males are not the choices of the females, then we have our two separate, two different matchings. Okay, any other questions about from TMA? Okay, I want to speak about question. No, I want to speak first about the question with dynamic array. Actually, so I'm constructing a new array that whose size is in question part C of this question. And again, there are and There are various ways to solve this question. I think that mine obviously is the best, or at least the quickest. So I want to show you how I suggest that you'll solve it. But again, it's not the only way. So what happened is that we start with an array of size, say 1. The next, when this is full, we are going for an array of size 1 plus alpha times 1, so 1 plus alpha. The next one will have size of 1 times alpha. And after I fill this array, it will be, I multiply this array by 1 plus alpha once again. So it would be 1 plus alpha square, 1 plus alpha cube, and so on. And at the end, let's assume that my last array had size of, the last array, the one that I created in the last step, has size n. So what is the size of the array that I created just before the very last one? The last one is has size n. What is the array that I created? What is the size of the array that I created one step ago? Recently I created an array of size n. What was there an array one step ago? Exactly. Jacob said, Danielo said, Jacob said, if at every step I multiply the size of the array by 1 plus alpha, that's when I'm going naturally in time, increasing the size, then one step ago, I need an array of size n times 1 over 1 plus alpha, right? Because if I take an array of size n times 1 over 1 plus alpha and multiply it by 1 plus alpha, I'll get the current time. And every time that I create a new array, the new size is by 1 plus alpha larger than the previous side. Okay, so that was the size of the one step ago. The size was, but I write right here, and since I'm a bit lazy to write 1 over 1 plus alpha at each iteration, let's call this number beta. So beta is just 1 over 1 plus alpha. And now I look at this sum of operation and ask how much time did I spend for the whole process. So let's write it down, and I'll go again backward in time from the very last step where the array was the largest size until the very first step long time ago when the array had size 1. So currently the size of the array is n times 1. One step ago, what you don't see here in the square, the size was beta times n. Remember, 1 times 1 over alpha times n. So beta times n was what I had one step ago. 2 steps ago, it was beta square times n. 3 steps ago, beta cube times n, and so on. Where beta, this number, is of course smaller than 1, because 1 over 1 plus alpha, alpha is larger than 0, so beta is smaller than 1. So we look at the sum and we said, hey, isn't it the whole sum that you keep torturing us with this sum through the whole course? And I said, yes, this is exactly the same sum. For example, if beta equal half, as will be the case in the next question, if beta is half, then the sum is just 1 plus half plus quarter plus 1 over 8, etc. This is the total number of summation. Because beta is smaller than 1, let's it go all the way to infinity. So this constant is just the sum of geometric terms. We saw it already in the examples that I showed in the first class. This is just 1 over 1 minus beta. 1 minus whatever this number is, 1 over 1 plus alpha. So why don't I just call beta 2 and why don't I call beta half, or making alpha equal 1, making beta equal 2, and I insist that you'll see the case of different beta is because practically it gives you a nice tunable parameter that you can adjust to your wishes. If you take alpha here, the factor by which you increase the size of the array, multiplicative factor by which you increase the size of the array, if you take alpha to be 0.05, for example, you are still getting a constant right here. So the overall algorithm is still of linear size, but then this term is much larger. You're spending much more time, but in return, our array consists of parts that is occupied and part that is free. And if you are short on memory, then you can trade memory for running time. You'll take alpha to be tiny. The size of the array will only increase. You're only wasting 5% empty space, but in return, the running time, you'll have to do these expansions much more frequently and waste much more time on it. And that's tell you exactly what it is. On the other hand, if you don't have any limitation of memory, then of course take alpha to be larger, 2 or 3. And of course the big application of dynamic arrays, as I mentioned, was when we are looking at hash tables and we don't know ahead of time how large is the size of the hash table. But so we'll start with a small array, and as the array keeps increasing, we will add more elements. From time to time, we will allocate a new array. That's actually how dynamic array in Java is implemented. Except that if we are using it for hashing, then we are not waiting until this array is completely full to expand it. We don't want load factor or that is close to 1, because the hash table is, if you remember, the time for open addressing hash table is depending very deeply on the load factor. I'll use alpha, the find time in hash, in open addressing hash table, was 1 over 1 minus the load factor, n over m. How many slots, how many keys divided by how many slots in the table. Right? Very exactly the same sum as this one. Meaning that in the message home from the hash table, I'm just reminding, was that we want n to be smaller than 2m. Small or equal. We need to have at least 50% of the hash table empty to have a really fast hash table, which implies that if we want to use the same principle for dynamic array, we are not waiting until the array is half full. We are not waiting until the array is completely full. We will expand it, double its size, when it reaches the limit of it's more than 50% full. At this point, we will double its size. Questions? And D, of course, here is a horrendous idea to run. If you're adding just say one cell at each expansion, then the overall running time will be in D. In D, if you're just adding alpha at each iteration, then the overall running time would be, say, if I'm adding just one cell, but to extend it by one cell, I have to copy the whole array into a larger array. And then a larger array just by one cell. Then the overall running time would be, once again, 1 plus 2 plus 3 plus 4 plus dot 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 n, the the algebraic sum, which is n squared. So bad idea. It means that every insert takes on average n time. Okay, question 7. We have the faucet turning off the handle to one side, turning off the handle to the other side. I thought about this problem when I got tired to, my house used to be on Airbnb, my rental, and I had a few showers in this house, and I got very tired to explain to tenants at each time which direction each shower you need to put for the hot water, and it was never the same. Every shower has its own direction. I had three showers in the I had 3 showers in the house, and each of them, the hot water was on different direction. And if it doesn't make sense to you, it doesn't make sense to me either, but that's how it was. And so I needed an algorithm that you can find the direction of the hot water with guarantees, no matter which direction the hot water is. So the idea was, of course, you'll assume that it's not less than a second, and you'll say, I'll put the faucet on the left for 1 second, and then I'll put it to the right for 1 second, and then I'll put it for 2 seconds, 2 seconds for 4, 8, 8, dot, 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 until eventually this number 2 to the I is larger than T mean, the minimum times that I would have turned the shower to had I known to what is a hot, which side the hot water coming from. So when 2 to the I is finally larger than T mean, then this process terminates, and let's see how much time this whole process takes. Let's call this time, denote it by n. That's the time that we waited in the last part. And let me just sum up the time that I spent on the right side. And then I'll double it by 2, and this is roughly the time that I spent in the left side. So if this number is n, that's how long I left the faucet to one side, to the right side, in the very last iteration. Then the overall time that I spent was 1 plus, what is this? N over 2. How much, what is this? N over 4 plus dot dot dot. So this number is just 2. Now you are looking at the fine details. You see that actually you might wait in the last iteration more 2 times T mean, because T mean is not necessarily a power of 2, and then I have to multiply it also by the left side. So all in all, what I'm spending is 2 times 2, 2. The overall time that I'll wait as a very quick analysis would be 2 because of the 2 sides times 2 for the summation times 2t mean, giving us a constant of 8t mean. You can improve upon this constant, but at least that's a nice friendly constant for our purposes. And it's exactly the same analysis that we did in the case of the dynamic arrays. People, questions? Anything else from this homework that you want me to check? You didn't see it. Excellent. Let's talk about a, let's start talking. Yeah, Shane? Question? Okay, let's talk about, let's continue with dynamic programming. Okay, I'm still not fluent with OBS. It's not window capture, it's window captures. Perfect. Dynamic programming. So I want to mention two lessons that we got from the discussions about the discussion that we had for the discussion that we had for the shortest path, because shortest path is, once again, it's nothing but dynamic programming, and I mentioned it multiple times that we can think about it as a hierarchy of problems, and to solve problems that are follows from vertices that are very close to the solution. We are going to use our solutions for small problem to generalize it for larger problems. Once again, the cut and paste lemma, I told it many times. Once again, if S and T is the optimal path to T, the shortest path to T, we have multiple ways to go to T. We are asking what is the solution to the subproblem of go just from U to V1. Solution is stick to the very same shortest path, just delete the beginning at the end, because had you had a shorter way, you can only keep, you would reach from U to V1 using the red path, then this would also be a solution for the larger problem of going from S to T. And another lesson that we are going to recycle is that it is enough to store just the very last vertex. When I'm running Dijkstra or Bellman-Ford or BFS, any of these algorithms cares about the global shortest path. But when I'm updating what each vertex needs to know, it needs to know or update with very little information all it needs to know is about the all it needs to know is about what is the cost to reach it. That is, V1 has to know what is the cost for reaching V1, and that will allow me to know at the end what is the cost to reach T. And furthermore, T needs to know only what is its predecessor, pi of T1, along the shortest path. And this data might be updated during the algorithm. Pi of T1, the predecessor, might change, but to reconstruct the path from S to T, I don't know the path directly from S to T. I find what is the reverse path by going backward along this path. I'll ask T, what is the predecessor to you? And T will say, this is V1. And I'll ask V1, what is the optimal path to you? And because of the cut and paste lemma, the shortest path to T, if it was go through V1, they have the same predecessor, which will be V2, and the previous of V2 will be this anonymous node right here, and so on. And that's how I find out what is the path from S to T, just by updating a constant amount of information. That's kind of clever, because otherwise, every time that I had to update a vertex, I had to tell this vertex directly what is all the path to you. So every step would have implied omega n information to be updated. And we're going to use these lessons when we'll talk about other dynamic programming problems. So let's define what is a subsequence in a string. We have a string, say X, which is A, B, C, D, sequence of letters. Every subsequence of X is a sequence that is obtained by S by possibly I'm allowed to delete some characters, but I'm not allowed to swap the order of any characters. So it's not a subset, it's subsequence. That is, AAC is not a subsequence right here because it means swapping C and A. So ABC is a subsequence. I get it by deleting C and so on, including ABCA itself, the whole subsequence. It's still considered subsequence. Let me also define what is a prefix of X. We'll denote the prefix of X as X, but with square brackets 1 ... M is the prefix that is obtained, the subsequence that consists of exactly the first M characters of X. So if X is, once again, ABCA, then X of 1 ... is the first 4 characters of X, which means the whole of X. X1 of ... is ABC. X1 ... is just AB, the first 2 characters. X1 ... and X1 ... is the empty set, the empty string. I'm going to use these sequences quite a lot. In the chapter of dynamic programming, our first 4 problems that are quite similar in the way we approach them. And I didn't see it in any textbook. So 2 of these problems, at least, you'll need to rely on the slides or other resources. These 4 problems all have to do with sequences and subsequences, except that in 2 the problems would be geometric, not problems of letters of strings. Instead, we will talk about curves and polylines. So, but all these 4 problems, namely the longest common subsequence, the edit distance, the dynamic time wrapping, and the Frechet distance, discrete Fauché distance. These are all 4 problems that we are going to approach with the same step of mind, the same attempt. So, longest common subsequence, LCS. We have 2 sequences, A and B, X and Y, sorry. We are allowed to connect only B to B. We want a matching which would be monogamous. B is allowed to match only to B and only to one other B. C is allowed to match only to one other C, and so on. But we want this matching to avoid any crossing. That is, we are connecting the characters by segments, and we want the longest set of segments that we can fit. However, every character is allowed to be matched only to one other character of the opposite side. And that is, this A cannot be matched to this A and this A at the same time, only to one of them. At the homework, I'll ask you questions that have to do with what happens if I'm willing to change this definition a bit. And that the order will be the same, which means that the set of segments that I'm going to push in this way, it defines a subsequence of X, which is also a subsequence of Y, and what I'm after is find the longest such subsequence, or more accurately, a longest such sequence, because it might be that I can reach that I have more than a single solution, more than a single longest common subsequence. Problem is clear. You're given 2 files and you want to find a matching between these 2 files and to ask what is common between these 2 files. You have DNA of 2 creatures and you want to ask what is common to their DNAs. And the DNA consists of bases, A, B, G, D, and you are asking, you're saying they are really similar if I can follow these sequences and there is a lot of commonality. The next problem that we'll discuss, the edit distance, will concentrate on finding the distances between what is the differences between the 2 strings. LCS tries to maximize the commonality between them. So it's related but different problems. Okay. And once again, a longest common subsequence, not necessarily the only one. Brute force algorithm generate all the subsequence of X, check each and every subsequence of X, and check if it's also a subsequence of Y. Now, if I give you a subsequence of X and I ask, is this a subsequence of Y or not? It's very easy to check in linear time. You just need to go simultaneously on both sequences and asking if one is a subsequence of another. That's if I generated such subsequences. How many subsequences of X can you generate? Or give me an algorithmic way to generate all subsequences. Help? Help, but I don't see my... where's my chat? My chat went away. You need to speak. Somebody, please. How many subsequence can I generate? How many subsequence of X can I generate? And where is my chat? Yes. Either I have a problem. Here is my chat. Okay. If somebody try to speak, I cannot. Uh, more, more. How can I generate all these subsequences in algorithmic way? I mean, you are very kind to X and assuming that this number is small. It's but you need to think about which algorithm would you use to generate a subsequence of, what did we have? A, B, C, D, E, and I want to generate every subsequence. And as I said, to generate a subsequence, you cannot swap the order of any characters, but you are allowed to say delete this one, so delete this one, and delete this one, and delete this one. So if you delete the A and C and D, you are left with B and D. So
Could you take like a recursive backtracking approach?
I don't hear anybody, but it might be because I put it on the wrong direction, my volume.
I asked, could you take a recursive backtracking approach?
Say again, please. Now I know which direction.
Recursive backtracking to find all
I can do it recursively, absolutely. And how many will you get? Give me a formula that tells me how many can I get.
I think it's either like n factorial or n to the n. I'm not sure.
You're in the right vicinity, but no, it's none of them. The only decision that I have to make about C is should it or should it not be deleted. We'll mark it as 0 if we don't delete it, or 1 if we do delete it. And the same decisions I'm making for A, the same decision for B, the same decision for each and every character. 2 to the n, that's correct. We have, it's good because I have good memory. I have very bad memory for names, so it's nice that the same 4 people are the ones that are contributing everything, but you should all remember that class participation count. Okay, 2 to the n is the right number because, or 2 to the m to be precise, if x is in order m, because I need to decide for each one of them if it's 0 or 1. So there are 2 possibilities for A times 2 possibilities for B times 2 times 2 times 2. So it would be, since I have 5, it will be 2 to the 5. So what we just described as an algorithm to find the LCS is not very efficient, right? Because once I generate a subsequence, it takes linear time to check if it's also a subsequence of Y, but that's the number of subsequences, as Danilo said. So that's the overall running time of the algorithm. And we want something more efficient. So toward a better algorithm, I'm going to worry at the moment not what is the subsequence, but what is the length of the longest subsequence. What's the philosophy? If you remember, when we ran Dijkstra, we concentrated first on how do I compute the length of the shortest path, And once I have an algorithm that can compute the length of the shortest path from S all the way to T, and I know this distance and the pi values, I could also backtrack and generate the path itself. But what governed my decisions was the length of the shortest path, not who is the shortest path. I'm going to use the same philosophy. I'm going to forget about what is the subsequence that I'm going to generate directly. I'm going to say, let's see an algorithm that computes the length of the longest common subsequence. And once I'll have this algorithm, I'll be able to backtrack in a very similar way to what I had in the extra. I'll be able to backtrack and generate the path itself. We need a bit notation. You don't like it, but we have to. So you have a sequence of character S. The cardinality of S with 2 bars on the side, means what the length of this subsequence. Okay, so that's the length of the subsequence. You remember that we talked about prefixes 2 slides ago, and I'm going to make a new definition, and it's going to look unfriendly. I'm going to look at the LCS of a prefix of I characters of X. Remember, X from 1 dot I is the first I characters of X. Similarly, Y from 1 dot J is the first J characters of Y. I'm looking at the LCS between them, the longest common subsequence. Put bars on the side to denote that this is a number now. It's a length. How many characters do you have in the LCS, or how many segments? And we give it a name. Cij is the length of the LCS of X, the prefix of the first I characters of X, the prefix of the first I characters of Y. Why am I going through all this gymnastic? Is because I want to express the solution to bigger problems with a solution of smaller problems. And I and J will start when they are very small, and slowly make their way to larger and larger I and J, that is longer and longer strings. What does a user need? The user wants to know what is the length of the LCS between the whole X and the whole Y, which is just, in this notation, is C of M, because X have M characters, and N because Y has N characters. The prefix of N characters of X is just X itself. Let's look at a recursive formula. I want to tell you there is some optimum out there. There is some maximum number of segments that I can stick between X and Y, and some solution here will work. I know that there is some solution, and for the moment I'll pretend that the last character of X is I, because I have the problem of looking at the first I characters of X. So let's assume that I is actually the very last character. What's come after I don't know, I don't care. I look at the first J characters of Y. Let's say what's come after the Jth, I don't know at the moment. My problem is find the maximum matching, the maximum LCS, maximum number of segments that you can stick without crossing between X and Y, but only this part of Y and only this part of X. And now I tell you that in addition to it, besides that I'm only cared about the first I and the first J, I tell you Xi contains A and Yj contains B. And actually I don't tell you that it's A and B, I just tell you that they are not the same character this character xi is different than the character yj, which implies that I cannot match between them. You'll see in the next slide that life are better when if I can match between them, but they are not the same character, so I cannot match them. What does it tell? What does it mean? It means that possibly in the optimum solution for this subproblem, not a big optimum solution, just the optimum solution to this subproblem, there are a few possibilities. Maybe neither this character nor this character are matched to anybody, and I can just concentrate on the beginning of the strings. However, it's possible that this character, the b over here, is matched to some character in x, but this other character, it cannot be xi. It must be somebody that comes before xi, because xi contains a and yj contains b. We are under the assumption that xi and yj are not the same character. So it's possibly that xi contains a, and that xi, this a is matched to some a over here, and yj, this b, is matched to somewhere over here in an optimum solution. Maybe both optimum solutions exist. Yes? Question? But as you see, we said that they are not allowed to cross. Right? And see that if I'm trying to match xa and yg and xi, yj to somebody beforehand, there is no, these two segments have no alternatives but crossing each other. So it cannot be that my optimum solution matches both the xi or the yj. One of them in this subproblem have to give up. So maybe I can erase the b over here, and then what would I do? I'll match all the I characters of x, that is this a and some anonymous character before that. I have two such matchings. That is, and I don't match the xi at all. So I leave it, at least for the time being, unmatched. So what is the length of the solution in this case? I am not matching this b, so I'm matching the first I characters of x, not to the first j characters of y, but to the first j minus 1. I gave up about the b. Only the first j minus 1 characters of b are matched to the whole of x, at least up to a. That is, so Cij in this case, if I give up about the b, then Cij, the first I characters of x, will be matched to y from 1 up to j minus 1. 1 to 1 all the way up to j minus 1. Move backward one step. Possibly that's the optimum solution so far. Or possibly I will give up about matching this a, so that one of them I have to give up. I'll give up about matching this a, and in this case I will match the first I minus 1 characters of x, match the first I minus 1 characters of x to all the characters of y, including this b, so this b can be matched to somebody. Only the first I minus 1 characters of x to all the characters of y, including the b. So remember, this is a smaller problem. The i's and j, the I minus 1 and j, it's a simpler, it's a smaller problem, earlier problem than the ij problem. There is fewer characters in the I minus 1 j and in the I j minus 1, both of them are somehow sub-problem of the ij problem, where I have the whole of x and the whole of y. So what did we see so far? I can give up on matching xi and match the first I minus 1 characters of x to all the j characters of y. What is the length of this solution? It is hopefully ready for me. It is a subproblem that I'll call ci minus 1j, and maybe I know this number. In this example, this number is 3. I have 3 segments that are in x I minus 1 and y all the way to j. There are 3 characters, 3 segments over here. See the length of the LCS of this subproblem. What happened about forgetting taking all of x all the way up to I, but match it only to the j minus 1 characters of y? That is, I'm giving up on matching the y, so this b is no longer with us. I can only match the previous characters. This b, so I have to delete this segment. So the length of this matching will only be, if I delete the b, then but a is included. Well, that's the highest such matching would be use these 2 segments or use other 2 segments from here, but exclude this very last one. Either way, the solution will be only 2. So which of the 2 solutions should I take? The one that uses 3 segments, right? That was C I C I minus 1, skipping this one. So Ci minus 1, comma, whole of j. So I'm deleting this segment. So this solution will have only, so this solution, as we see, have 3 segments in it, or the solution that has only 2 segments. The Ci j minus 1, give up on matching the b. Which of the 2 solutions should I take? Well, no rules. I'll just see which one of them give me more segments. One has 3 segments, the other one has only 2 segments, so I'll just pick the maximum, implying that Cij, the length of the matching of the whole string to the whole string, in the case that xi and yj are different, Cij is nothing but the maximum of Ci minus 1j and Cij minus 1. Just to see that I didn't lose you completely. What is x equal a, b, c, d, and y equal a, b, c, d, and my question is what is c of 3, 0? Just to see that you guys understand the definitions. C of 3, 0. I'm trying to understand. People? Just to remind you what the definition, Cij is the length of the longest common subsequence of x of 1 dot I, first I characters of x, to y of 1 dot j, first j characters of y. And my question is, what is C30? So it's a bit annoying answer, and I agree with Cole that your answer makes more sense, but according to what the law says, when we looked at the definition of a sequence, x of anything 1, 0 is just the empty string. So it was a bit a trick question. 3, 0, I'm taking from Y the first the first 0 characters, and I'm trying to match them with segments to the first 3 characters of X first, to the ABC, but from Y I'm not taking any character, so this is of course 0. So I cannot match anybody. And it doesn't matter what I write over here, it's still 0. Let's take a more interesting example. Let's take a B, A, B, and I'll ask now a bit more interesting question. Let's ask what is C of 3, 2. C of 3, 2. I'm taking ABC and the first 3 characters of X, and I'm matching it to the first 2 characters of Y, to the BA, and whatever I find, this matching should not cross. The order should be the same. So I have 2 options about what do I want to match. I can decide that I'll match the B with the B, or, and this is exclusive or, I can decide to match the A with the A, but I cannot take both, so either way the answer will be 1. Make sense? That's because subsequence will be obtained by I delete somebody. So either I delete the B's or I delete the A's, but I cannot do both. What would be a C of a 4, C of 4, 3. The answer is 2, right? Because I'll connect this B with this B, and I'll connect C of whole of 4. I'll connect this B with this B, and A, B, C. No, sorry, it's still sorry. I'll connect this A with this A. Yes, this A with this A. This will be with this B. Yeah, fine. 2. Okay. People, you start to feel comfortable with this notation. You know, this notation is a macro to a long speech. I first decide which part of X, always a prefix, then I decide which part of Y, always a prefix, and then I start putting my segments only between these 2 parts, and Cij is just how many segments I can stick in between. So far I expressed something in terms of something else which didn't make us much clever, and also didn't tell us whom to match with whom. The next case is is more positive. So again, I assume that X ends at the problem with AI. AI is the last character, and I want to match all the characters of X. I want to match all the characters of Y only up to the jth character, but in this case Xi and Yj are the same. So what can I do? The argument is that what happens if I match them to each other? Since it's the same character, I can match this A to this A, and remember, I ignore everything that happens in the future. I don't care about what happens in the future. Maybe what I'm doing now is devastating to what I'll do in the future. I don't care. Nevertheless, so my world right now only concentrated on the first j characters of Y. The last character in this sub problem is xi, yj, and the characters they contain is the same character, a for example. What happens if I match them? Could I cross any previously created segments? No. I cannot cross this segment, cannot cross any previously made segment, but the question is the cut and paste lemma. How should I match now xi minus 1 to the yj minus 1? Right? I already decided that x, as far as I know, consists of something and then a, that's in the ith index. I already decided that y consists of something and a, that's in the j segment. And now I have the subproblem of how to match the first j minus 1 characters of x, the first j characters of x, the first I minus 1 characters of x, the first j minus 1 characters of y. Remember, my problem is a larger problem. I cared about whole of x and the whole of x. And I ask, how should I match this subproblem and this subproblem such that together with this segment, I'll get an optimal matching of everything? And the answer is, it's a cut and paste lemma once again. You will find the best you can do when you're matching the first I minus 1 to the first j minus 1. Find the best matching to this smaller problem that only I minus 1 and j minus 1 are involved. And this local optimum is part of the global optimum, at least the global optimum for that includes I and j. That is, if xi and yj are the same, then cij is just ci minus 1 j minus 1, the optimum to the two subproblems, plus 1 of connecting this very last segment. Right? So this tells you eventually what should you do, which segments you're going to connect. And now, how is the whole thing is going to happen? Because what the decision that I'm making right now might be a stupid decision. Take this segment altogether. But now I'm saying, let's try during the algorithm, where the algorithm is going is, let's try all the combinations of I and j. And we know that in the optimum solution, somewhere for some I and j, my solution consists of segments. These segments don't cross each other. Here is my optimum solution. I cannot put more than 4 segments in my optimum solution. In the optimum solution, there is the last segment that is matched. That is part of the matching. For some I and j, I will match xi to yj. And how should I match the rest of the problems? As if I and j is the last segments of the whole thing. That is, applying exactly this recursive formula. Since in the optimum solution there is I and j that obeys the correct solution, then if I'll just check all the combination of I and j, and indeed we are going to check all the combination of I and j, and for each one of them ask what is cij, we will for sure hit the optimum last segment, which recursively will use the previous last segment, which recursively will use the previous and the previous. So we will be able to connect all these segments out there. The code is going to be really, really simple. The ideas behind it are not. It takes time to get used and takes time to generalize to other questions. But just to flash with what is going to be the code at the end, the code at the end is going to be just initialized, and now for every I and every j, if xi and yj is the same character, then cij is just c I minus 1 j minus 1 plus 1. Do this trick. Otherwise, xi and yj is not the same character, then cij is just a maximum of ci minus 1 j, ci j minus 1, what we saw in the theorem where at the beginning. And that's the whole code after a long speech. Questions? Perfect. We'll continue Tuesday. Homework questions, by the way, homework 2, people started to take a look. Quiet. Thanks, everybody.